Yes, welcome you all for today classes. So in this today classes we are going to start the new topic, that is infinitesimal stage efficiency or polytropic efficiency in a compression processes. So compression process can be takes place in the compressor. Okay, so that infinitesimal stage efficiency or polytropic efficiency. So both are same in compression processes. So a finite compressor stage can be viewed as it made up of infinitesimal number of small stages. So if you are taken one compressor, so that is a finite stage compressor. That there is a finite is nothing but countable stages. Countable stages. So in that we have to made it of infinitesimal number of small stages. Again we have to divide it, that is one stage, into a number of small stages, that we call it as infinitesimal stages. So each of these small stage has an efficiency eta p. So each of these small stages has an efficiency eta p is called as a polytropic efficiency or infinitesimal stage efficiency. So first you can take one finite compressor stage or finite stage compressor. So that stage can be divided into a number of small stages. So that is called it as a infinitesimal number of small stages. So each of these small stages has an efficiency eta p. Okay, is called as a polytropic or infinitesimal stage efficiency. Okay, consider a single stage compressor having stage efficiency eta s, having a stage efficiency eta s, operates between the pressure P1 and P2. So that divided into infinitesimal stages. So you can take one single stage compressor. That stage can be divided into a number of stage, and that stage total stage compressor is having the efficiency eta s, and it is operates between the pressure P1 and P2. So that is divided into a infinitesimal stages. Okay, next, see here, the consider one intermediate stage that operating between the pressure P and P plus dp, P and D plus dp, and the temperature T plus temperature T and T plus dt. So efficiency of such stage is called as a polytropic efficiency. Efficiency of such stage is called as a polytropic efficiency. Okay, so now you have to take one uh, single stage compressor. That single stage can be divided into a number of small stages. That we call it as a infinitesimal stage of infinitesimal stages. Okay, that single stage compressor having the pressure P1 and P2. So in between that pressure P1 and P2, again we divided it into a small stage. So that those pressure is called as a P and P plus T, and the temperature T and T plus dt. So this is called as a polytropic efficiency. Okay. For this we have to take this temperature versus entropy diagram. So this here we can take our single stage. This is a 1 to 2. It is just one stage, single stage compressor. So in this, it is operating the pressure between the pressure P1 and P2. So this is a single stage compressor. It is operating between a pressure P1 and P2. So again, these single stage compressors can be divided into a number of small infinitesimal stages. Okay, so out of that infinitesimal stages, we can take that one stage that operated between the pressure P and P plus Tp. So we can take one stage in between the pressure P1 and P2. So that stage pressure is P and P plus Tp, and the temperature is T and P plus dt. Okay, so this shows the compressor temperature versus entropy diagram. Okay, so first we know that the polytropic efficiency is equal to isentropic temperature rise divided by actual temperature rise. So in this, what is isentropic temperature rise here? So this TD, T, T, sorry, DT is the isentropic temperature rise. Okay, and this TD, this from this point to this point, it is the actual temperature rise. Actual temperature rise. This is a isentropic temperature rise, and from this point to this point it is an actual temperature rise. That will give us the polytropic efficiency. So that you can write the TTS stage efficiency, isentropic efficiency divided by actual temperature rise. dt is equal to dTs divided by, so just we have to take this term and this efficiency term is coming in this side, so neta p dash. Again we have to write that dt is equal to, so this dTs can be written as p dash minus t divided by eta p. So dt is equal to t, just we have to take this t term outside, so into the bracket what we write, t dash by t minus 1. If you have taken this t to the outside of that bracket, then it becomes minus 1. T dash by t minus 1 divided by neta p. Okay, again we have to write that dt by t, just we have to take this t divided by t, then it becomes dt by t is equal to t into, okay, t into, so we know that t dash per t is equal to, if you are writing this in terms of the pressure ratio, then it becomes what, the pressure limit of the pressure is here p and p plus dp. So for that we have to write p plus dp by p raised to gamma minus 1 by gamma minus 1 divided by eta p. Okay, so next dt by d is equal to 1 plus dp by p. So the p by p it becomes 1, just we have to separate these two terms, p by p plus dp by p. P by p is nothing but 1, dp by p gamma minus 1 by gamma minus 1 divided by eta p. So for these equations we have to use the series of expansions. Series of expansions, it is used in your mathematical. Okay, so that using series of expansion, okay, 1 plus x raised to n will give us the 1 plus nx plus n into n minus 1 by 2 plus or minus so on, and neglecting the higher order of that 1 plus nx. So if you are applying this expansion, series expansions to the above equations, this dt by d, so we will get that, suppose if you are consider this x, 1 minus x here dt by dt, so this is becomes our n. Okay, so here 1 plus, and this will get cancelled here, so this minus 1 plus 1 will be cancelled, directly I can write that nx. So in place of n we are having that gamma minus 1 by gamma here 1 plus x raised to n, in place of 1 is nothing but this, okay, dp by p is nothing but x, and gamma minus 1 by gamma is nothing but what, n here. So in place of n we are having this gamma minus 1 by gamma, so that we have to substitute all one. Okay, this one and this one get cancelled here, so we'll have to take n is equal to what, gamma minus 1 by gamma. Okay, so 1 by neta p, so this is into 1 plus gamma minus 1 by gamma into dp by p minus 1. Okay, so this is the dt by d is equal to 1 divided by neta p into minus into bracket gamma minus 1 by gamma dp by p. Okay, so again this is simplified to this term. Okay, so now integrating the above equations, pressure from T1 to P2 and the temperature T1 to T2. Okay, integrating the above equations, pressure T1 to P2 and T1 to T2. So if you integrate this, dt by dt becomes what, ln of T2 by T1 is equal to 1 by neta p gamma minus 1 by gamma ln of P2 by P1. So eta p can it can also be written in terms of what, holotropic efficiency, that is neta p is equal to what, gamma minus 1 by gamma ln of P2 by P1 this. Okay, so divided by this term to this side, just we have to take this eta p and divided by ln of T2 by T1. So also we can write this ln of T2 by T1 is equal to what? 1 by eta p gamma minus 1 by gamma ln of P2. So you can write that ln of T2 by T1 is equal to ln of P2 by P1. So just we have to take it as term in the above. So it becomes what? 1 by n eta p gamma minus 1 by gamma. So theta 2 by theta 1 is equal to ln gets cancelled. If you write this theta 2 theta T2 by T1 is equal to what? P2 by P1 is 2 1 minus eta P into bracket and gamma minus 1 by gamma. This is equation number 1. So, assuming the irreversible adiabatic compression process 1 to 2 as equivalent process with an index of compression n. Index of the compression here, if you are taken instead of this gamma, you can take that index of compression that is represented with the n. Just you have to write that T2 by T1 is equal to P2 by P1 n minus 1 by n. So this is equation number 2. So comparing the equation number 1 and 2, so we got that 1 by eta p gamma minus 1 by gamma is equal to what? N minus 1 by n. So comparing 1 and 2, we get that. So T2 by T1 is there, P2 by P1 is there. Here also T2 by T1, P2 by P1 is there. Just we have to comparing these two indexes. We get that 1 by eta p gamma minus 1 by gamma is equal to n minus 1 by n. So the eta p is equal to gamma minus 1 by gamma into bracket n minus 1 divided by n minus 1. So hence there are two formula to find out the polytropic efficiency for the compression process. So what are those? So these equations are very important to find out the polytropic efficiency of the compressions here. So first formula we can use that in terms of pressure and temperature. In terms of pressure and temperature, so if there is no, he has not given any indexes, that compression index which is represented with the n. So that time we have to use this pressure and temperature terms. So that is given by eta p is equal to gamma minus 1 by gamma ln of T2 by T1 divided by ln of T2 by T1. Similarly for second, eta p is equal to what? Gamma minus 1 by gamma into bracket n minus n divided by n minus 1. So these two formulas are used to find out the polytropic efficiency for the compression process. Okay. Similarly for infinitesimal stage efficiency or polytropic efficiency in expansion process that takes place in the turbine. The expansion processes takes place in the turbine. Okay. A finite turbine stage can be viewed as it made up of infinitesimal number of small stages. Again, we have to take that one stage of the turbine that can be divided into a number of small stages, that we call it as a infinitesimal number of small stages. Okay. Each of these small stages has an efficiency eta p is called as a polytropic or infinitesimal stage efficiency. Okay. So again, next consider a single stage turbine having the stage efficiency eta s. Okay, and operates between the pressure P1 and P2 that divided into infinitesimal stages. Okay, so you can take that single stage, that final stage turbine. So that stage is operating between the pressure P1 and P2. So in between these two pressures, we have taken again one small stage that is called, that stage is operating between the pressure P and P minus dP. P and P minus dP. Okay, and temperature T and T plus dP, T plus dt. Okay, so efficiency of such stage is called as a polytropic efficiency. So efficiency of this, whatever the stage is there, it is in between the pressure P1 and P2. So we can take that another small stages, that stage is operating in the pressure P and P plus dP, T and T plus dt. Okay, so that stage efficiency is called as a polytropic efficiency. Okay, so that will show the temperature versus entropy negative. So again we have to write that polytropic efficiency can be written as actual temperature rise divided by isentropic temperature rise. Again we have to write that actual temperature rise is dt by dTs. So again we have to write dt is equal to eta p into dTs. Again we have to write that dt is equal to eta p into this dt d Ts can be written as T minus Ts, that is the temperature between the actual temperature and the isentropic temperature. So that again we have to write that dt is equal to neta p T into, so if you are taken this T outside, then you will be left with 1 divided by Ts by T. So again this we have to take this T to this side, then it becomes what? Pt by dt. Okay, net P into 1 minus. So if you write this temperature ratio in terms of the pressure ratio, we get that P minus dP by V into bracket gamma minus 1 by gamma. So bracket complete. Okay, dt by T is equal to what? Neta P 1. Again P by P is get cancelled here. P by P minus dP by P. P by P is nothing but 1. So minus dP by P raised to gamma minus 1 by gamma. Bracket complete. Okay, so here just you have to separate these two terms, you will get this term. Again using the series of expansion, that 1 minus x raised to n is equal to 1 minus nx minus nx plus n into n minus 1 by 2 factorial into x raised to x square. So minus n into minus 1 into n minus 2 divided by 3 factorial. So by using these equations, we have to apply these equations to the above equations, that dt by t. So if you are observing or if you are comparing this with this, so what here n is equal to what? Gamma minus 1 by gamma, and dp by p is nothing but x here. So that is 1 is here, it is 1 is there. So neglecting the higher term, that 1 minus x we have to neglecting. So applying this expansion, series of expansion to the above equations, we get that dt by t is equal to neta p, it is as it is. So this one is as it is, minus, so if it becomes what? Minus 1 minus nx. So n is nothing but what here? Gamma minus 1 by gamma, this is gamma minus 1 by gamma. So this x is nothing but what? dp by p. Okay, so this is neglecting the higher term, just we have to neglecting the higher term. So this one and this one get cancelled here, so that dt by t is equal to what? Neta p, we left with gamma minus 1 by gamma into dp by p. Okay, just simplification steps are there in this derivations. Okay, so again we have to integrating the above equations, the pressure p1 to p2 and temperature t1 to t2. So get that dt by t is equal to what? Ln of t2 by t1, which is equal to neta p into gamma minus 1 by gamma ln of p2 by p1. If you are integrating these above equations, you will get this equations. Next we have to write it in terms of what? Neta p. Just we have to uh, just you have to shift this term to this below. Okay, so ln t2 by t1 divided by just you have to take this term to this side, then it becomes what? Gamma minus 1 by gamma into ln of p2 by p1, that is the polytropic efficiency. Okay, so next it can also be written as ln of t2 by t1 neta p gamma minus 1 by gamma into ln of p2 by p1. It can also be written in terms of what? Ln of t2 by t1 is equal to ln of p2 by p1 raised to neta p into gamma minus 1 by gamma. Just you have to write it in terms of indexes. So that t2 by t1 ln get cancelled, t2 by t1 is equal to p2 by p1 into bracket np into gamma minus 1 by gamma. This is equation number 1 here. Okay, so next, assuming the irreversible adiabatic compression process, expansion process 1 to 2 as a equivalent, so this should be expansion process here. Okay, expansion process with an index of compression expansion n. So just write this. Instead of gamma, we have to write the n here. Then it becomes what? T2 by T1 is equal to P2 by P1 n minus 1 by n. Comparing the 1 and 2 indexes, we get that neta P gamma minus 1 by gamma is equal to n minus 1 by n. So that neta P is equal to again what? Gamma minus gamma divided by gamma minus 1 into n minus 1 by n. This is another formula for the polytropic efficiency. So we can use two formula here to find out the polytropic efficiency for the turbine here. Neta P is equal to what? Ln of T2 by T1 divided by gamma minus 1 by gamma into ln of P2 by P1. So this is one formula to find out the polytropic efficiency for the turbine. So when you have to use this, if you are he has given the temperature and pressure limits, then we have to use this formula to find out the polytropic efficiency for the turbine. If you have not given, then it becomes what? Another formula, gamma by gamma minus 1 into bracket n minus 1 by n. This is another formula. These two formulas are used to find out the polytropic efficiency of the turbine. Okay, so this is wrong now. So we have to write this. Instead of this, we have to write these equations. Okay, this is about the polytropic efficiency for the turbine as well as the compression. Okay, so please watch this video, and if you have any doubts, you can contact me. Okay, thank you.